And hello from the campus of Carnegie Mellon University in Pittsburgh, Pennsylvania. We welcome you to the Software Engineering Institute's webinar series. Our presentation today is Architecting Software in a New Age. Depending on your location, we wish you a good morning, a good afternoon, or good evening. My name is Shane McGraw, your moderator for today, and I'd like to thank you for attending. For any questions you have pertaining to the presentations today, we will address all questions at the end of the second presentation. So you can log your questions at any time within the webcast or console, but we will address all questions at the end of the second presentation. We're also going to ask a couple polling questions throughout the day. In fact, we're going to launch our first polling question for you to answer now. And what we'd like to know is, how did you hear about today's event? So take a couple seconds to answer that. While you're doing that, I'd like to point out another 3 tabs that you're going to see on the console, and they are the Files tab, the Twitter tab, and the Survey tab. The Files tab has a PDF copy of the presentation slides there now, along with other software architecture related conferences and training from the Software Engineering Institute. For those of you using Twitter, be sure to follow @SaturnNews and use the hashtag SEISWArch. Once again, it's @Saturn_news and hashtag SEISWArch, as in software architecture. Now I'd like to introduce our first speaker for today. And the first talk is going to be Trends and New Directions in Software Architecture by Linda Northrup. And Linda will speak from 1:30 to 2:15. Linda is Chief Scientist of the Software Solutions Division at the SEI, where the technical agenda comprises architecture-centric engineering, software development and acquisition practices, measurement, software product lines, cyber physical systems, advanced mobile systems, and ultra-large-scale systems. Linda is co-author of the book Software Product Lines, Practices and Patterns, and led the research group on ultra-large-scale systems, or ULS, that resulted in the book Ultra-Large-Scale Systems, The Software Challenge of the Future. Now I'd like to turn it over to Linda Northrup. Linda, all yours.
Thanks very much. I am absolutely delighted to be giving this webinar. And what I'm going to be talking about is software architecture. Now, for those of you who don't know much about software architecture, you will understand something about software architecture, its importance, and why we believe it's critical to the quality and longevity of a software system. For those of you already savvy about software architecture, I hope that you will come away with some new perspectives about trends and challenges that we face in architecting today's systems, as well as some of the practices and current research that we'll address. So basically, it has long been our premise that the quality and longevity of a software-reliant system is largely determined by its architecture, and many studies have led us to that conclusion. There are many things we see in systems like communication bottlenecks under certain loads and difficulty in integrating and testing and adding new features, and all of those actually are rooted in some architectural decisions that don't support the needs of the system. In fact, I will posit that architectural considerations are absolutely key to quality of a software-reliant system. Now, software architecture is not a new concept. In fact, people have been talking about software architecture since the 80s. The whole idea was introduced because systems were becoming much more complex, and the behavior we were expecting of those systems was much more demanding. And so we needed to reason about the system at a level of abstraction. So over the years, people thinking and talking about software architecture, it's always been about structure, it's always been about abstraction and quality attributes. On our website, you would find about 150 definitions of software architecture. The definition we use is that the software architecture is a set of structures needed to reason about the system, which comprise the software elements, the relations among them, and the properties of both. But basically, one might take Martin Fowler's expression. He says, architecture is basically the hard stuff. It allows us to make engineering trade-offs. And in fact, many have said that the focus on software and architecture brought engineering to software systems development. Well, what do we trade off? We actually are trading off the functionality. Of course, we need the functionality, but what else? What we call quality attributes. Those are all those properties that the system is needed to have in order to be assumed to be of high quality, like performance and interoperability and modifiability and the like. And the problem is you can't have all of these, and so you need to make trade-offs. It is the architecture that actually allows us an abstraction to make these trade-offs. And oh, by the way, these quality attributes need to be characterized for particular systems, and they're not just arbitrary handles that we select. They're derived particularly from the business goals, the mission goals of a system. So if a business goal is to increase market share, for example, then you're going to need a system that's scalable, and that certainly has demands on the architectural decisions you make. So if we think about a system, we have some business and mission goals, and we'd like to implement it, develop our software, and get the system that satisfies us. But we really have no evidence, no guarantee about how that's going to occur, whether it's going to occur, and what trade-offs we've made. So in fact, the architecture is that mechanism, that abstraction. Now you might say, well, I use frameworks, I use open source, I pick my technology stack. I don't really have an architecture. Well, you have an architecture, you just might not know the one you have, and you might not be using it to the advantage that you could in order to analyze the system and make appropriate trade-offs. We've been espousing our views on software architecture over the years. Our books all have this in common. They focus on quality attributes. They link to business and mission goals. They have this rooting in an interaction with stakeholders, whether those are supply chain partners, testers, customers, developers, managers. And most importantly, they're rooted in quality attribute models, formal techniques, real-time scheduling techniques, reliability mechanisms, usability frameworks, and the like. Over the years, a lot has happened in software architecture, architectural patterns and styles that allow us a vocabulary for design and analysis, component-based approaches that can take a containment or a container strategy with interfaces that make assumptions about quality attributes, company-specific product lines that have architectures that allow us to manage the variation at the same time, capitalize on commonality, and then model-based approaches where architectural models are used to generate code. Most recently, frameworks and platforms that form the basis of ecosystems where the communication protocols are of paramount importance. And all of this has evolved into standard interfaces that are used in architectures for families of systems that need to interoperate. But a lot has changed. Beginning with the web in 1997, everything has changed. Everything has changed in terms of connectivity. We are an infinitely connected world where there are not only internet connections, but huge webs of wireless connectivity and autonomous devices. And all of this has grown to actually planetary scale and complexity that flies in the face of old hierarchical ways of controlling systems and developing systems. We're awash in data. There's a tempo, there's an appetite for speed that we see not only in the marketplace, we see it in system development, we see it in government, and there are all kinds of ecosystems that rely on one another, so one cannot operate in a stovepipe. Also, if you listened to the U.S. State of the Union message last night, you heard a tremendous focus on cyber defense. Everyone is concerned about vulnerability because we are connected and because we are so exposed and because software is so prolific. And there is also this whole notion of collective action, where humans, through social media and wireless technology, join forces with computational elements and autonomous elements to form a society that is very new. Against this landscape, there's a whole blush of disruptive and emerging technologies. They're seductive, they're prolific, from Google Glass to social media to cloud computing to 3D printing. And a whole wash of software development trends. I'm sure many of you are engaged in the open source strategies, NoSQL, machine learning, and all of the rest that I have there. And so one might focus on any of these, and we could spend an afternoon talking about any of these, worthy of discussion in the relationship with software architecture, but I'm going to ratchet it up to a higher level because I believe that the technical challenges could be boiled down to 4. We think about accelerating capability. Everybody is talking about velocity, continuous integration, continuous deployment of many systems where we're getting thousands of releases in very short time periods, but also accelerated development and deployment of what I'd call deliberate systems, planned systems, ones that aren't released multiple hundred times a day. And then also the need to get software code incorporating innovations. So new innovations happen. We don't want to wait a 10-year period to get those innovations into our code. So likewise, we have a need for software assurance. I've talked about thinking about free from vulnerabilities, but software assurance means more than that. It actually means that the system's going to behave the way we intend it to behave, to do what it's supposed to do, and things that it's not supposed to do shouldn't happen. It should cost what we expect it to cost, and it should be able to go live when we time it to go live. So assurance about all of those things. And then there's scale. Scale in all types of manifestations, whether it's lines of code, number of processors, number of users. We have applications now that are very commonplace, that have 500 million to billions of users. This is very, very different. It's data, it's computational elements, it's people involved in the system. This is a very different level of scale than previous systems have encountered. And then thinking about evidence that what you're doing is going to work for accelerated capability, software assurance, and scale. Greg Wilson from Mozilla, in a 2012 blog, wrote that evidence is not the plural of anecdote. So we need much more than a story that says, it happened here. We need scientific evidence, we need proofs, we need simulations, we need situations where we have statistically sound samples that say certain techniques will work for your objectives. Now here's the rub. Each one of these is a challenge, but the intersection, systems that are fast, at scale, and are assured, that's the real challenge. And you can't have it all, so there are trade-offs in these intersections, trade-offs in the structure of the systems, the process, the time, and the cost. And as I mentioned, architecture is that mechanism for making trade-off analyses. And so I would argue that architecture is the enabler for trade-off analyses, very important in our brave new world where we have these challenges. So what I'm going to do for the remainder of this overview is take a look at each one of these challenges and the relationship of architecture to that particular challenge. So when we think about accelerating capability, everybody does want high velocity. Everybody wants to be agile. Agile with respect to balancing structure and flexibility. Agile with respect to being able to cause change and respond to change. We want to be agile in our software practice. We want to be agile in our businesses because we live in a dynamic world. So many people have sort of cast architecture as big document-driven approach. And they think about, well, if we focus on the architecture, there is no way we can be agile. Jim Highsmith, who is viewed to be one of the founding agilistas, if you will, gave a wonderful keynote at a conference called Saturn in 2010, in which he took on this topic of architecture and agile. And he said there's a difference between being agile and doing agile. And he said agility is enabled by architecture, not stifled by it. But in the process of being agile, in the process of taking an incremental approach to architecture, we have to be careful not to accrue what I'll refer to, and many people refer to, as technical debt. So we often, when we are fielding a system, make some decisions, whether they're architectural decisions or code decisions, to take a shortcut because we need to release. We can't afford the cost of delay. And those decisions result in increased complexity in the system, more difficulty in changing the system later on, and possibly some quality issues. Now, Ward Cunningham in 1992 gave this situation a name. He used the metaphor technical debt because he was trying to justify the need to refactor a system to some non-technical product management stakeholders. And so one can think about debt, and we all make these decisions. One's mother is ill, and you need to go see your mom, but you don't have the money for the plane ticket. So you charge the money for the plane ticket. Now, as a mom, I would argue you need to make that trip. Charge it. But it goes on your credit card. Now, if at the end of the month you don't manage that charge, you accrue other charges because you need to make other decisions and pay for other sorts of trips or luxury items. Eventually, you get to the point where your credit card is maxed out. And it isn't easy for you to respond to emergencies. It's not easy for you to purchase that plane ticket. You have to somehow manage the debt. And so it is with software. In fact, if the technical debt increases, your ability to change the system decreases, and actually the customer responsiveness, or your ability to respond to customers, decreases. And this is problematic. So you don't actually see technical debt, you only see evidence of it. And the evidence of it becomes visible when you're trying to add new functionality or new features, or when some defects or low quality become apparent. And again, this can be architecturally rooted, it can be code rooted, but the whole idea is you need to have a prudent plan to understand the risk you're taking on, to avoid accumulating excessive technical risk, and to actually manage the technical risk. We all need to take some at some times. We all need to accrue some technical debt because you can't afford the cost of delay. But being prudent about it is what's important. So people in the Agile space like games, and we at the SEI made a little game that you can simulate the software development life cycle, and you can understand the concepts of uncertainty and risks and options and technical debt by playing this game. You can download it from our website, and you can use it in a classroom or in a work setting. On a more serious end, we are doing research. We're building a workbench. We're using architectural abstractions, field studies, some conceptual correlation modeling to build a workbench that would allow organizations to see the technical debt they have and to manage the technical debt over time. So there's a very large community organized around technical debt right now, people who are building tool sets, people who are building dashboards, and it is a concept that is very important for anyone who takes an incremental approach to system development and needs to understand ramifications of architectural and code decisions that they make in order to avoid the cost of delay. Now, let me give you a little bit of an example. You might say, well, can you do incremental development with a focus on architecture? Can you do architecture incrementally? I'm going to tell you a very quick story. And this story is about the Mexican Stock Exchange. So the Mexican Stock Exchange approached the SEI, actually Bursatech, which is the technology arm of the Mexican Stock Exchange, was tasked with building a new trading engine, because the decision was made not to buy an off-the-shelf trading engine, but to replace the 3 that they had. And Bursatech committed to deliver this trading engine in a little more than 2 years. They asserted that it would be high performing. They wanted it to be a higher performing, in other words, faster than the previous engines they had, but they also wanted to be faster than their competitors, faster than NASDAQ, the London Stock Exchange. Such a system has to be highly reliable, as you would understand, and high quality, and it's got to be scalable because there are peaks and ebbs in stock trading, and the system has got to be able to withstand high loads in trading volume. So the SEI's role was a coach. We coached the Bursatech team, and we worked with the principles that we espouse, namely our architecture-centric engineering approaches, which you can read about, and also the team software process. And this is a familiar diagram that I showed you earlier about the role of architecture. And we wickered this with the various SEI architectural techniques. We used TSP as the scaffolding for team management, project management, and measuring. And I just want to show you very quickly some effort charts so that you see that architecture was actually spread across the 6 cycles of development that were used. In the beginning, we did architecture design, and we did some UML detailed design, and we did some prototyping. We needed to understand what was possible, and so the prototyping was important. We did very little requirement solicitation because we started out with basically replacing the engine systems, stock trading engine systems that actually existed. In the second cycle, there was much more of an architecture emphasis, much more requirements. We did a lot of coding in UML diagrams. And we did actually a skeleton of the system so that we could test out the communication between the various components in the architectural design. In the third cycle, we actually stubbed out the system, and we did a fair amount of performance testing, going end to end to see what the throughput could be. In the fourth cycle, we didn't actually keep effort metrics, but we used this to rethink garbage collection and collect some things that needed to be done. In the fifth, we actually had a day trading system, full functionality for day trading. We developed the testing framework, the testing, and we begin to admit the new requirements for the things that were to enhance this engine stock trading engine. And finally, in cycle 6, we delivered the complete system, which was not only the day trading, but the maintenance at night, the startup, the actual maintenance and logging that was done. There was still some architecture, still some requirements. If you add up all the effort overall, only 15% was spent on testing, which is very unusual for this type of system development. Now, let me give you the punchline. Was Bursatech able to deliver on what they promised? Yes, actually, they were able to deliver ahead of time with hiring no increased staff, and I would add that many of the people we coached were not seasoned architects by any stretch of the imagination. What's really impressive is that the performance was 300 times faster than the actual performance of their earlier stock trading engine, faster than NASDAQ, and faster than the London Stock Exchange. What I have here before you are numbers that are publicly available, but I know that the situation is actually even better than what's publicly available. And the quality, 0.1 bugs per case lock, which is very unusual. In this type of system, we would see 0.5 to 1. Since the system has been launched, there has only been one software problem and it was easily remedied. So in fact, the architecture was developed incrementally. The quality of the system was delivered as expected, in fact, exceeded expectations. It was delivered on time, at cost, and we did it incrementally and used the architecture to perform the analysis that was necessary in order to deliver on the quality attribute agenda. Okay, now let me switch a little bit. Most people are able to handle incremental development, and a lot of people are incorporating architecture techniques in their incremental development. If you haven't, I hope I've given you some insights into how to do that. But let me switch to DevOps, because the focus now is on deployment. Even though people can handle incremental development, there are problems with deployment. And the mantra these days is velocity, continuous integration, continuous deployment. And so we need to understand how to pick up where our agile development left off. So the state of the practice in DevOps is focusing largely on culture and teaming. There are a lot of processes that are used to monitor status checks, tooling, dashboards, a tremendous amount of tooling to understand the architectural health, to understand the runtime performance, the operational performance of the system. And all of this is working quite well, and there are a number of organizations who have really gotten on the DevOps bandwagon and are doing well with it. And yet, you can still be blindsided. You can be blindsided by frameworks that you've chosen or tech stacks that you've chosen for your system that don't allow you the deployability that you need for your continuous integration and continuous deployment. And many of those decisions are not a matter of refactoring, would require that you would actually have to replace hardware, would require substantial and topological changes in the software. So one of the things you need to focus on if you are interested in a successful DevOps strategy is to think about it early on, to think about deployability at the architecture stage, to understand that in order to have a system that will meet your deployability expectations, you're going to have to think about what your deployability scenarios are and pick architectural tactics and make architectural decisions that will actually support testability, deployability. You need to think about wiring into your system monitoring mechanisms so that during runtime you can actually monitor the health of the system. These are architectural decisions. These are architectural strategies. It's too late to think about these once you have already developed the system and move into this operation phase. So you have to blend the development and operation, and architecture has got to be part of the conversation. Now let's move to the second challenge, which is scale. I've given lots of invited talks about scale, and in fact, one of the titles that I've used over and over is Scale Changes Everything, which is not a hyperbole because in reality it does. When you have systems of the scale that we're talking about, this sort of planetary scale involving humans and autonomous entities and computational devices, we see that the situation requires distribution of development, distribution of data, distribution of evolution. We see heterogeneous software and hardware. We see unprecedented connections, unprecedented use of systems. There are many, many challenges. And I could talk about scale for a long time and have, but I'm going to focus on three issues related to scale, and in particular related to architecture and scale. Cloud strategies for mobility, and big data. So when we think about cloud computing, and almost everyone is using cloud computing because we have these warehouse of computational capability that we can tap into through web services, we have to understand that the cloud provider and the cloud user have potentially very different business goals. And because the quality attributes are driven from the business goals, potentially different quality attributes. So one might argue that Okay, but we have service level agreements so that all is copacetic between the cloud provider and the cloud consumer. However, the service level agreements are a minimum and they can't prevent failures. So what we have to do as a cloud consumer is architect our systems knowing that we don't have full control over many of the important quality attributes. Specifically, cloud providers are going to optimize on reliability. They want to provide consistent computational power to the cloud user. They want to provide a level of acceptable performance, which is usually articulated in the SLA. At the same time, their trade-offs have to do with energy efficiency. They're paying for electricity and cooling of these massive server farms, and this is a non-trivial issue that factors directly into their business goals. So you're the cloud consumer, and you like the reliability you're getting and the performance, but now you say, but I'm really concerned about security. I want to make sure that nobody hacks into what I have in the cloud. Whoa, that's a trade-off. And you need to think, when you're architecting your system, how you're going to compensate for what the cloud provider is not going to provide to you that's not necessarily articulated in the SLA. So you need to be smart about cloud computing. Ian Gorton, who is one of our colleagues, has said that cloud computing allows us to fail cheaper and faster than we were able to before. So very important to think about architecture when you're using cloud strategies. Now, the world has moved to mobile device. There's a huge mobile device trend, and we're now using our smartphones, we're using our tablets as ways to connect with the internet, as ways to connect with social media, as ways to control our appliances and devices. And we've come to expect a level of performance because we're used to laptops, so we think our tablets and our mobile phones are going to have the same sort of capability as our laptops. But the reality is they are limited in size, they are limited in battery power, and there is some variance in the latency between your mobile device and the cloud that you're gathering your enterprise data from. And if you're using this mobile device for something that is critically important, like triaging some sort of health situation in an emergency event, you want a little more reliability than what you can typically get with mobile devices today. So what are some of the architecture trends? Well, architecture trends today are in what many people are calling cyber foraging. One trend is edge computing, where we push the computation, the data, the analysis to the very edge of the network, to the people who are using these mobile devices. This sort of computing we find is necessary for early responders, for soldiers in war situations where they have a mobile device, a handheld, a tablet, and they need to do some analysis, and they need computational power, and they need data staging, they need a way to get data from the cloud. So we appeal to some surrogates, maybe some nearby laptops that will allow us to augment the capabilities of the mobile device, so we can offload some of the computation, so we can do some of the data staging there, so the data coming from the cloud can in transit be hosted in this surrogate, in the laptop, and then move to the mobile device. Industry is starting to build on this concept to improve mobile user experience and decrease network traffic. Our experience and our research is in cloudlets. Cloudlets are virtual, machine-based, forward-deployed servers. They're located a single hop away from the mobile device. And what we've been able to do is allow the mobile device to operate in disconnected mode, where we're in a war situation and the mobile device totally disconnects from the network and from the enterprise. But the cloudlet is able to be provisioned so that it provides the continuity that's needed in these situations that are high stress and high criticality. One other related to scale is big data. And I'd be really remiss if I didn't talk about big data, because everybody's talking about big data. But when we talk about big data, there are trade-offs from the network on down. And again, you guessed it, architecture is a very good abstraction for us to reason about those trade-offs. Now, a little bit about big data. There are really two distinct but related technology thrusts. There's the data analytics, how you want to analyze the data. The data is usually heterogeneous. It comes from lots of different sources and is big volume but low information content. And what we want to be able to do is analyze it so that it's high information content and low volume. So people use a combination of machine learning, they use static analysis, and there are lots of algorithms that people are employing for data analytics. The flip side is the infrastructure. You need infrastructure to house this big data. You need infrastructure to actually perform the analysis and the computation. And that infrastructure has got to ensure that the analytics are fast, they're scalable, they're secure, and they're easy to use. So basically, you've got a big filtering problem. Now, the state of the practice is that the big data problem is not solved. We know that companies like Amazon and NASDAQ and Google and Facebook and Netflix are way ahead of most of the rest of us. If you work for those organizations, you're in an enviable position. But these organizations have also been at it for about a decade, and they've also pumped billions of dollars against this problem. Most other organizations have not been able to enjoy that kind of a lead time and that kind of a pocketbook. But even so, these big organizations have had some problems that many of us have experienced, like the Christmas Eve 2012 Netflix outage, Amazon's August 19th, 2013, 45 minutes of downtime that lost them $5 million in revenue. Google's homepage offline for 5 minutes on the 16th of August in 2013. And I think most of us have already heard about NASDAQ with Facebook's IPO in June of 2012. So lots of problems. In fact, there was a study by Infosys that 64% of companies admit to having big data initiatives, but only 55% of them have no strategy for doing so. So we know there are some big challenges here. When you're thinking about architecture in big data, the trade-off here is between capacity and cost. We want capacity, but most organizations can't afford the capacity that they actually need. They want tremendous scalability, but as the systems become more complex, as the analysis becomes more complex, there are trade-offs with scalability. Most people use NoSQL models, and those are not all created equal. So some of them have different data models, different query models, different consistency. And the other thing is you need to be able to monitor during runtime what's happening with these big data systems, otherwise you can't manage them. All of these are really big challenges. We've got some research. I have some URLs at the end of the talk to direct you to. One of them is called Leap for Big D, where we're actually providing a risk reduction decision support system that allows people to input their quality attribute requirements and a spectrum of the NoSQL technologies that they're looking at, and this provides you some support for what the best choices are. We're actually building this into a knowledge base that continues to grow in knowledge using machine learning techniques, and we call this K-base. So everything I've talked about actually is about software assurance, because we're using the architecture to, in fact, provide assurance that we're going to get the right behavior, to perform the engineering trade-offs between the various qualities that are most important to us. And this gives us a level of assurance, provides us evidence that we can count on the system. We can count on the system as it's built, as it's deployed during runtime. Now, Rick, in his next talk, is going to focus more on security, which is often interpreted as software assurance. I admit to a broader definition. But I wanted to end with a little bit of a focus on software assurance, because I haven't yet said much about how architectures are depicted. What do we use? Well, basically, you need enough detail in what you're depicting to do the analysis that you're trying to perform. And that can be informal, from Visio diagrams, to formal architecture languages that have precisely defined execution semantics. When we're talking about safety critical systems, when we're talking about systems that are internal to our engines of our automobiles or in avionics, we need more. Informal models are not sufficient. And so we need the formality, because we understand from lots of studies, this is a chart from one of them, that in these sorts of systems, this is from the avionics industry, that the cost of air vehicles is increasing dramatically, and the amount of software in those air vehicles also increasing dramatically. And what we see is faults that leak through the system and tremendous task of testing and integrating the system, almost prohibitive. And so what we need to think about is how we can use the architecture early on and do some formal reasoning so that we actually can eliminate some of those faults and preclude them from leaking through the life cycle of the system. So one effort is a language called the Architecture Analysis and Design Language, or AADL, which the SEI has been involved in. And this language provides grist for doing that sort of formal reasoning. In fact, provide a semantic model that allows us to express quality attributes in a formal way and to be able to reason about all of those quality attributes using formal mechanisms and make the appropriate trade-offs. We, with this technique and this language, have been able to perform what's being called virtual integration, so that before the system is developed, we can actually make trade-offs using these architectural models, virtually integrate the system, and identify lots of problems that would only be detected downstream in integration and test previously. So these are the kinds of techniques that can be used to provide the level of software assurance that you need in safety critical systems, and they're based on formal architectural modeling. So let me conclude by saying that if you thought that software architecture was an old idea, something that started in the 80s and maybe was best left to the early 2000s before our brave new world of social media and cloud computing and mobile computing and all of the rest, I hope I've convinced you that the principles of software architecture and their importance persist. The challenges are different, but the need to be able to do ongoing analysis to do trade-off analysis is still very keen, and the demands on our systems are much higher than systems of the past, and in fact, the systems themselves are much more prolific and much more important to life as we know it. So there's a lot to be done. What I see in the future are much more fluid architectures, much more tool support, adaptive architectures, architectures with lots of runtime monitoring built into them so they are capable of internal monitorability. And I will stop there. I hope this has provided you sort of a whirlwind perspective of not only where we've been, how important architecture is, but some of the important challenges and the relationship of architecture to those challenges. So thanks very much.
Linda, thank you. That was a terrific talk. And Linda's going to stick around, folks, for the Q&A after Rick's talk. So she'll be here for any questions that came through during that part of the presentation we'll address in a few minutes. Just one quick housekeeping item to address. A number of questions came in about recording and the availability of the slides. The event is being archived. The login will be the same that you used today. It should be available at some point tomorrow. An email will go out letting you know when the archive is up, and it's the same login process as today.